Hi, my name is Jing. I'm a first-year PhD student at Chalmers University of Technology. I'm presenting our research on hierarchical reinforcement learning based on planning operators. When a robot is assigned a high-level goal, such as stacking boxes, it must autonomously determine the sequence of actions required to achieve that goal. For example, the long-horizon goal of stacking boxes generally requires 5 steps to complete. Tasks that need multiple steps to accomplish are defined as long-horizon tasks. We draw inspiration from the fields of reinforcement learning and symbolic planning to address such challenges. Reinforcement learning is a machine learning method in which an agent learns by interacting with the environment, taking actions, and receiving rewards or punishments as feedback. The agent iteratively improves its decision-making to maximize cumulative rewards over time. In the following part, I will use a simplified example, window block, to illustrate the main drawback of reinforcement learning during state transition, which makes it difficult to learn the optimal sequence of action. This video shows an unsuccessful experiment using reinforcement learning. The figure on the right illustrates the state transitions, with states S1 through S5 representing the different stages in the process and the transition between them. For instance, in Markov decision process, consider a scenario where block 1 is lifted in the current state. In long-run tasks, due to the probabilistic nature of state transitions, reinforcement learning faces challenges in learning the optimal sequence of actions to achieve a goal. The same action can lead to different subsequent states at different times, and this cumulative uncertainty over a long sequence further complicates the learning process, because the RL agent must explore various sequences without guidance, and since Markov decision processes neither capture historical information nor detect execution failures, it becomes difficult to learn an optimal policy for the action sequence. Or if the sequence cannot be learned correctly. Thus, the key point is how to improve sequencing in reinforcement learning. One way to solve this problem is to use some definitions from symbolic planning. Generally, symbolic planning involves a domain model, which encompasses the object types, predicates, and possible actions within the model. The problem description specifies the exact object that exists and their current state. Each operator is assigned specific preconditions. When these preconditions are met, the operator is considered applicable. Upon successful execution, the operator produces certain effects that describe the resulting changes in the environment. Given this information, an external solver selects appropriate operators to achieve the task goal. PDDL is an example of symbolic planning. Continuing with the previous example, once block 1 is lifted, the current environment state becomes the precondition for the next operator. In this situation, the current state satisfies the precondition of the operator move. Agent will start to execute the new operator. While symbolic planning is efficient in high-level reasoning, its main drawback is the lack of specificity in low-level control, which is crucial for precise execution. Based on this analysis, our hypotheses are long-horizon tasks can be split into simple and independent policies. If the complete operator definition is appropriately defined, then they can be efficiently chained together to achieve the desired task goal. Based on this hypothesis, we propose a novel learning method that combines hierarchical reinforcement learning with planning operators to learn independent policies. Based on preconditions and effects, this method automatically constructs the sequence of actions. We introduce the concept of operators into the definition of Markov decision process. Like traditional method, we include definitions for the set of states, state transitions, reward function, and discounting factor. In this framework, O represents a set of key operators, where each operator has its own specific precondition and effect. The variable A represents the low-level control policies used to execute an operator. Again, use the operator move as an example. The precondition determines whether move is the appropriate choice for the next step. The low-level policy A attempts to execute move. For example, A is a 4-dimension vector, where 3 dimensions represent translation movements from one position to another, and the 4th dimension describes the grip action as open or close. Since the action A changes the environment state, if move is successfully achieved, the current state will then reflect the effects of the operator move and can satisfy the next operator's precondition. This figure presents the entire process of our proposed method. Initially, given an environment, we can observe several pieces of information such as block position, velocity, and etc. This observation is state-based. Preconditions are used to describe the observation as predicates, and then the high-level reinforcement learning agent uses these preconditions to select an appropriate operator. Each operator has a unique ID, which the low-level agent uses for indexing during learning. We use the soft actor critic method to compute the low-level policy. It receives operator ID and the observation from the environment. At each time step, we evaluate whether the operator has been successful or not, based on predefined success criteria, and give rewards corresponding. High reward for success and low for failure. Then start the next trial. Our approach, which combines hierarchical reinforcement learning with symbolic planning, yields good results in enhancing the sequencing of reinforcement learning. Our method found that the minimum number of operators required for the successful execution of long-oriented tasks, here are stack and insert, is 0. On average, the number of operators used ranges between 6 and 7 across different tasks. In cases where issues such as block falling or incorrect insertion positions occur, the RL agent can still reach the final goal by automatically increasing the number of operators. 2 kinds of experiments are used to evaluate our method. The first experiment assesses whether our method can efficiently and accurately chain independent policies to accomplish long-oriented tasks. In this case, while the definitions of basic operators remain the same, we introduced task-specific operators like stack and insert. The high success rate in achieving long-oriented tasks confirms that our hypothesis, splitting and chaining policies, is both feasible and effective. The second is to evaluate the learned independent policies. Here, simple policies mean RL with heuristic planner can achieve. Our method outperforms the baseline with higher success rate and a much more stable performance. Complex policies are long-oriented tasks. Heuristic reinforcement learning cannot handle them, even when using pre-trained models. This representation and relations of symbolic operators are knowledge that comes from humans. There exists an implicit relation with human experts. We also compiled our method with imitation learning baseline, behavior cloning, which is explicitly learned from humans. Both experiments illustrate that our method has a better performance. In conclusion, operators enable the creation of holistic plans and can serve as independent policies. The results of our method demonstrate good scalability, as we can add more operators for different tasks and ensure that the sequence is interpretable. Importantly, this method makes the problem tractable. Our model can find a solution in a reasonable amount of time. The presented symbolic structure demonstrates competitive performance in achieving long-oriented tasks for reinforcement learning. Our code is freely available. Thank you for watching my presentation.